Welcome back to ECE 442-542. This session is concerned with preparing you for your second attempt on quiz number 5. And the way I'm trying to do this is order the questions roughly in the order with which they were scored the lowest on. Meaning the first ones that we will address are the ones that most of the students didn't do as well on, or maybe I should say the fraction of students that scored the worst on these questions are loaded towards the front of this review session. So the first one, with that said, is what pole locations, now we're thinking about a second order system with a 0 at the origin, you immediately can be thinking that you have this transfer function that's alpha z over some z squared minus az plus b, something to that effect. Now, what we can do is I like to think when we're starting to talk about these specifications, performance specifications, is thinking about it in terms of this grid that's marked off with angle indicators, and you can see then the 90 degrees, and now you've split this 180 degree half circle, and we'll just concentrate on the positive complex root, and we know that they do appear in complex conjugate pairs, so the conjugate will be below this, but we aren't going to focus on that. This angle, these angle indicators, there's now 10 of those, so now each of those represents 18 degrees since we're dividing 180 by 10, so now we have 18, 36, so that sort of gives you a feel for where you are at relative to an angle theta sub d. You also have these zetas, what we've been calling the heart shapes. Those are indicated, and you can see that the smaller hearts, which correspond to less overshoot, are shrinking or getting smaller as zeta increases from 0, which is the unit circle, all the way to the real line or the real axis, which is when zeta is equal to 1. So let's now work through this. It's asking for essentially the A and the B in this parameterized form of a second order transfer function, a percent overshoot larger than or equal to 10%. So now this is written a little bit differently than what you might think a percent overshoot spec needs to say. This is now saying, oh, you can have a percent overshoot larger than 10. So now we could have a 20% or a 30%. So this is now saying that relative to our breakfast cereal, this is now outside the heart. And what's the heart? Well, now we might, let me see if I can access some of these. We say a percent overshoot larger than 10%. I like to have this page in front of me, and if somebody says, oh, you want a 10% overshoot, now I immediately see that that's indicating a zeta of 0.6. If we now look at this, it says outside the heart. Well, now that 10% overshoot is saying zeta is equal to 0.6. We are now saying that we are somewhere above that heart. So we're now over here to satisfy that first specification. The second specification says a settling time T sub s less than or equal to 10 samples. This now says we are moving in the consistent direction that we're used to thinking. Now we want inside the circle. And 10 samples now, I'm trying to sort of work around all of this, but now you could just have this on your sheet, inside circle, and we know the relationship between the radius, and the number of samples. We're now given a performance, we want the pole. So we were given the performance spec, or N sub s, of 10. We can now calculate R based on that. So now that we have that, we can say, oh, let's now say that's now going to use this formula, and using that formula, now I have to remember what my number was, and I forgot to put everything down, so bear with me here while I try to calculate some of these values. But in this case, we're inside a circle, and we said N sub s, I think, was 10, wasn't it? So now we're trying to compute the radius that we will now be inside of for this settling time of 10 specs, and this is now 0.631. And obviously you're not going to be able to get that much resolution in your sketch, but now we have something. If I could draw a circle, oh, not a very good circle. We're a little bit beyond 0.6. And remember, we're above the yellow, we're inside this blue, and hopefully the next specification, which is the time to peak, this one also is a little bit backwards. This is now saying your time to peak is larger than or equal to 2 samples. This is now saying that our angle needs to be less than whatever the design spec says, which is 2 sample periods, and our time to peak equation. So now we are angle less than whatever this time to peak spec, and our time to peak spec is related in the analog setting to our damped frequency of oscillation omega sub d. But we also know the relationship between omega sub d and theta sub d, and solving that for omega sub d allows us to rewrite our peak time relationship as pi t over theta sub d. We were just told, and now I'm running out of space, that time to peak was bigger than 2t. And so this is now saying that we want an angle less than this. Let's solve for the angle. This is now pi t over theta sub d. We can cancel the t's. We now find that theta sub d is equal to pi over 2 at the upper limit. That now says that we are to the right, or smaller in angle, than 90 degrees. That was our pi over 2 in radian measure. So now we're looking for poles that are inside that particular region. And you could now look at those different poles that might have been provided to you, and one of those now might have been z squared minus 0.4z plus 0.29. And you could apply the quadratic formula and find those roots. You could also complete the square, which is useful here to see what the real part is if you're anticipating those being complex. Now we have z squared minus 0.4z. That's giving us what we needed in the first two terms, plus 0.2 squared, which is 0.04, and what's left over then to make up the 0.29 is the 0.25. And to get that, I hope you see what I'm trying to do. That's now 0.5 squared. So this is now saying that one of those poles is at 0.2 plus j 0.5. Or we are now, if I can find a different color, we're now saying that we have a real part of 0.2 and a vertical distance of 0.5, and that's lying right inside where we wanted to live. We wanted to be inside this green shaded area, and that now gives us the pole pattern or the pole locations that we needed. And if you look at the other possible second order polynomials, you will find that one of them, I believe, gives you a real part of 0.4, but then it actually gives you an imaginary component or a vertical component of 0.8. So you're way out here, and that's not in the green shaded region. Another one actually had a real part of 0.8. You're already outside of that green shaded region, outside the heart, that's formed by being outside the heart, inside the radius, and to the right of that angle theta sub d. This was our theta sub d angle, the upper value for that. So that's now how we arrived at the answer to this particular problem. I think it's enhanced in terms of your thinking through to just have this grid in front of you and start shading areas or regions that are consistent with these performance specifications, and then find the intersection of all three of those, and that's what I've tried to shade in green in this Z-plane grid. Hopefully that now helps with that lowest scoring problem. The next problem deals with finding a transfer function associated with the following step response. And you again can assume this is a second order and you have 1, 0 at the origin. The structure then is exactly the same as what we just had for the earlier. It's now alpha z over z squared minus az plus b, for example. And what can you see? And here I should have been a little bit more clear. This, I'm assuming, is a unit step, but I could have said, to make it a little different, I could have said, what about a input due to a constant input of, let's say, 5? Then you would have to incorporate that input of 5 versus here, we're assuming now our input is 1. Well, one thing that we can immediately see is that our final value of our response is at 4. Our peak value, which right now is a little suspect because we now have, here is t, here is 2t, and that point is 3t, and this point is 4t. So it's a little bit suspect. Where do we say our peak occurs relative to the period? And we also know, though, that our maximum or peak value of y is 5. So knowing all of that information, we can now create this transfer function g of z. How do we do that? Well, first off, we know that our final value, it's now occurred after the transients. You can see that it's no longer oscillating your response. So that's now the DC gain of your system times the input, which in this case was a 1. So now we know that 4 is equal to our DC gain times 1, or our DC gain, which we now can find by evaluating that g of z at z equal to 1, is now equal to 4. Well, we're not there yet because we don't know a and b, but once we know a and b, we can then find alpha from this DC gain argument. So now if we assume our time to peak is 3, which I did in reworking this, 3t, Now, comparing that to what we know it equals in terms of theta sub d, that's pi t over theta sub d, we can now solve that for theta sub d. The t's cancel, and theta sub d is pi over 3 in radians, or 60 degrees, depending on how you set up your calculator in angular units. So now we have a time to peak of 3 sample periods, which translates into a theta sub d of 60 degrees. Boy, if we just had the radius, we could find the radius by looking at our settling time. Our settling time, though, is a little bit suspect. How do we determine that we're within 1% tube of our final value of 4? So now it might be easier to deal with the percent overshoot, because we have y max, we have y final. That can be used to find our percent overshoot. Our percent overshoot then is y max minus y final over y final times 100%. And I know I'm going to run out of room, so let me just try to increase my, so I apologize if you're trying to take notes. You can, I guess, go get some scissors and tape and expand your piece of paper that I provided you with the note-taking material. But now we have 5 minus 4 over 4 times 100%, or that's now 1/4, or 0.25 times 100%. Our percent overshoot is now 25%. Again, I like to go to this curve. We now know that our percent overshoot is 25%, and we can immediately maybe see, oh, that corresponds to a zeta value of 0.4. And we don't have to get on our calculator too much. So now we can just say, okay, zeta is 0.4 based on our percent overshoot spec. Well, now we have theta sub d and zeta. We still don't have r, but remember, we can find that from this table that interrelates these 3 design or performance specifications. Our performance specification table says that if we have zeta and theta sub d, we can now come up with an r value in terms of zeta and theta sub d. And there's the formula. So now we can go back and we can say, oh, now that we have zeta and theta sub d from our table, we now know that r is equal to e raised to the, well, let me just say raised to the minus zeta theta sub d, and theta sub d needs to be in radians, 1 minus zeta squared. So if you plug in zeta of 0.4, don't forget to square it down below when you're taking it inside the radical. Theta sub d is pi over 3. You will end up with 0.633. Well, now we can say, oh, we now have z minus r e to the j theta sub d and z minus r e to the minus j theta sub d as our quadratic. Those are our 2 unique poles. We have one in the first quadrant. We have its conjugate in the fourth quadrant. We can now multiply that out, and we have z squared, and you will see this happens over and over again, that we have inside, we have r e to the j theta d plus r e to the minus j theta sub d plus r squared times e to the j theta d minus theta d, or that's now just r squared. The exponents cancel in that last product. Wow, I'm really running out of space. Maybe I should just leave that drawing window open. I may be giving you more than you wanted, but hopefully you see Euler sitting in here. You have e to the j theta d plus e to the minus j theta d. That's 2 cosine of theta sub d. So you now have z squared minus 2r cosine theta sub d. That's just some coefficient, z plus r squared. We just calculated r squared to be, we just calculated r to be 0.633. You square that, and hopefully you end up with 0.4. So now you're looking at your denominator polynomials in the answer and trying to find one that might have a 0.4 for its constant. If you look at this, you actually are starting to get a little bit inaccurate relative to this particular value. Because of that, now you might go back and say, well, where did we maybe have a point of confusion? And it's right there. Where do we sort of draw the line? Sometimes assuming it was 3t, sometimes assuming it's 4t. You don't really know. Let's now see what happens with 4t. That's kind of right in the middle. Maybe that is, in fact, where it hit its peak, its maximum of 5 in sort of the real world setting. So now if we said our time to peak was not 3 periods, but 4, now we end up with theta sub d being pi over 4. Makes a pretty big difference. This is now going to say that we have this is equal to 45 degrees instead of the 60 degrees. We now can say that our 2r cosine, that's a terrible r. I think I'm getting nervous because I'm running into that next question. And I apologize if you've already cut and pasted. You're going to really be frustrated now. But we now have 2r cosine theta d. This is now 2 times the 0 point whatever r was. Oh, so now we have to go back and redo the r, don't we? Because we assumed theta sub d the first time through was pi over 3. Now we have to create a new r, e to the minus zeta theta sub d over the square root of 1 minus zeta squared. With theta sub d being now pi over 4, this ends up being 0.7098. Now r squared is different, so maybe you couldn't find that 0.4 in the earlier answer. Now maybe you see a denominator that has a 0.5. The 2r cosine of theta sub d with this corrected r value times the cosine of theta d, which is a square root of 2 over 2, actually ends up 1, so that now we're looking at a denominator polynomial of z squared minus z plus r squared, which is 1/2. We're now almost home. We know g of z's denominator. What we don't know is that alpha, but we know how to find it because we now know the DC gain. The DC gain was g of z evaluated at z equal to 1. This is now alpha times 1 over 1 minus 1 plus 0.5. And we know that DC gain, so this is g of z evaluated at z equal to 1. This is now equal to 4, so that alpha is 4 times 1/2, or 2. And that should now help you find your g of z expression that is the appropriate transfer function for that problem. I'm not even paying attention to the time. Hopefully we're still okay a little bit. Suppose a controller C of z is z minus 0.8 over z minus 0.5 is applied to a plant, G of z, in a classical block diagram with negative unity output feedback. Now I'm assuming, boy, I did not give myself enough space to work these problems. Hopefully you have plenty of scrap paper that you can now write on. Now what you're interested in is we have the classical configuration. There's our controller C. Here's our plant G. We have a negative unity output feedback. There's the unity equaling 1. Negative is there. Here's our R and here's our Y. We're interested in the closed loop transfer function between y and r, and hopefully you can remember or rederive that that's now this cg over 1 plus cg. And we are given c and g 0.5 z over, what did we have? And you can see that this cancels that in the ZG product, and that's okay. That's a cancellation inside the unit circle. We then have in the denominator of this CG product z minus 1/2 times z minus 1. That's there. 1 plus, oh, I apologize. This is starting to frustrate me. I'm sure it's frustrating you more than it is me. So now let me move that down, give myself a little bit more space. But don't get frustrated during the quiz. Just plug on. You have plenty of paper. This is now the 0.5z, z minus 1/2, z minus 1. And that's what you had here and there. So those denominators are going to cancel. And we now have z minus 1/2, z minus 1 plus this 0.5z. We multiply this out. And we end up with z squared minus z plus 1/2. And that's actually the last polynomial that we had here. And that one, we knew what zeta was for that one. That zeta was 0.4. Where am I? So a zeta of 0.4 now tells us that we are here. Or we can now say, oh, this question was asking for the percent overshoot. We have a zeta of 0.4. Now we have a percent overshoot of 25%. So that would be your go-to value that you're looking for. What happened to all my work? I thought I had more work than that. So now this polynomial gives rise to a zeta of 0.4. That now, from our chart, says that percent overshoot is equal to 25%. Next question. Suppose a plant is given by G of Z, and one wants to control this plant using the Ragas-Eenie controller design approach. Suppose the desired closed-loop transfer function T sub C is to be designed to yield a settling time of 30 samples, which closed-loop transfer function would be valid for T sub C of Z. So now what you're looking for is G of Z. What's restriction 1? Restriction 1 says that we need to have a pole zero excess in our T sub C of Z consistent with the pole zero excess of G. So this now says we have a pole zero excess of 1. That's what this has. or more. Our pole zero excess could be larger in T sub C of Z. It just cannot be smaller. What about R sub 2? Restriction 2 deals with the numerator polynomial in our plant, and in fact this one does apply, and that says that we need in our T sub C of Z, we need to have its numerator needs to contain a Z minus 1.5 factor. So that now we know that T sub C of Z is equal to some alpha Z minus 1.5, and what else do we need? Or what were we given? We were told now that we didn't have a deadbeat response, we actually had a settling time of 30 samples. So that settling time of 30 samples now is back to this particular performance pole relationship. We now know that R can be found, the radius, by 10 raised to the minus 2 over n sub s. So now we can go back here and we can say, oh, we're getting close to what R needs to be in this denominator. R is 10 raised to the minus 2 over n sub s, where n sub s was 30, and that gives you an R value of 0.8577. Well, right now we don't have a pole zero excess of 1, we have a pole zero excess of 0, so this T sub C is not quite right. We need to increase the pole zero excess. We can put in a fast pole for T sub C of Z, which is what happens when we add them at the origin. What we don't have in this specification of a problem, we don't have any air steady state spec, so alpha could be anything you wanted. But one choice might be, what if we made T sub C of Z such that it had a DC gain of 1? And you can now use that to find the alpha, and that might then be one option and allow you to find a structure for T sub C of Z that has this for its slow pole, the dominant pole. We have a Z for the fast pole. We have to retain this factor to satisfy restriction 2. Restriction 3 didn't apply. We didn't have any unstable poles in G of Z. And alpha, one option to find that would be to allow the steady state air to be equal to 1. Next, if G of Z is equal to this transfer function and T sub C is K over Z, find the gain K in this T sub C of Z based on the Ragas-Eenie controller design. Restriction 1, that says that we have a pole zero excess of 1 or more. Looking at G of Z. G of Z has a pole zero excess of 1. We can have more than that in T sub C of Z. T sub C of Z right now has a pole zero excess of 1, so we're good for restriction 1. Restriction 2, do we have any unstable zero factors in our plant? Restriction 2 isn't applicable. Restriction 3, however, is. And there we actually need to make sure that 1 minus T sub C of Z evaluated at the Z where our pole is where we have that unstable pole factor at 1.5. We need that to equal 0 so that it will cancel that unstable pole in G of Z during our construction of the controller transfer function C of Z, so that C of Z doesn't try to cancel that. In this case, that now says that T sub C at 1.5 needs to equal 1. And t sub c of z at 1.5, that was k over z. We evaluate t sub c of z when z is equal to 1.5. We want that to equal 1. We can solve that for k, and that should be our answer. What is the appropriate or approximate settling time that results from a step input applied to the following system? Now, if we look at this, our denominator is what's going to influence our settling time. And if we think about this in terms of the polar form structure of our roots, now we have z minus r e to the j theta d times z minus r e to the minus j theta d. Again, that gives us that structure that we have seen before. That's z squared minus r e to the j theta d plus r e to the minus j theta d z plus r squared, and we know that from Euler is 2r cosine theta d. By comparing this parameterized form of our denominator, we can hopefully see that r squared is 0.72. R squared, not r. We now know that r squared is 0.72. R is the square root of that, which is now 0.8485. Now what do we do? Well, now we can go back to this relationship. We now know if we're given a pole and we're interested in settling time, if we're given a pole, we're given r's value, its magnitude. We can plug it into this formula to find how many sample periods it's going to take before we settle. In this particular case, then we say that n, and we can do this ceiling function, just take the next largest integer, minus 2 log, but I'm saying approximate, so it may be close to that, and this ends up being 28. It may have been a little bit bigger than 28, but I said, what's the approximate settling time? 28 was closer, hopefully, than any of the other answers. What is the approximate percent overshoot that results from a step input applied to the following system? So now this is exactly the same denominator that we had in the past problem. So let's now see what we can do here. Well, we can actually, with our denominator, we can again complete the square to help us figure out where we are relative to the real part and the imaginary component of this quadratic. We now have z squared minus 1.2z plus 0.72. Well, to find that minus 1.2 in the linear factor, we know that we could obtain that if we had something like that. Z minus 0.6 when squared will give rise to this z squared minus 1.2z, but it also gives us a 0.6 squared, which when we square 0.6 gives us 0.36. We need to end up eventually with our constant being 0.72, so we now need to add to this 0.36 another 0.36 so that the total here is the 0.72. Well, this is just 0.6 squared. So now we can put that information to use. We can say, well, we are at 0.6 for our real component. We are at 0.6 for our imaginary component. And in fact, that sort of looks like it's intersecting with a zeta value of 0.2. Now we can go to this percent overshoot and say, oh, if I have a zeta of 0.2, is that what I just said? Then I can find the percent overshoot, and that looks to be 52% from this curve. So now this zeta value from the curve or from the formula, you can plug that in, now gives us a percent overshoot of 52%. For the following step response, which denominator polynomial in a second order system with a 0 is most likely? So now we're looking for the denominator polynomial. Here, again, we need to count the periods to get us to our peak, because we need the denominator, we need time to peak, and again, finding the settling time is a little suspect here. How many samples does it take to settle? I can't tell what's 1% of 7 and find out what that sample is. So let's now use zeta from our percent overshoot and theta sub d from our peak time. There's t, here's 2t, and there's 3t. The hard part here is going to be, what is that value? Well, that's a little bit bigger than 9.5, let's say. So now we know that y max is 9.6. Let's just eyeball it. Our time to peak is 3t, 3 sample periods, and our y final is 7. All of that taken together, we now know this relationship between time to peak, that's 3t, is pi t over theta sub d. We've seen this before. Theta sub d is now pi over 3, or 60 degrees. We now know theta sub d. We now can find our percent overshoot. That's now y max 9.6 minus y final over y final times 100%. And there could be some uncertainty there because we're eyeballing that maximum or peak value of y. But just doing this eyeballing, this now says that we have 37.1%. We can now go over here and we can say, oh, what is 37.1%? Wow, that looks like it's at about 0.3. So from this, we can immediately say from our curve that zeta is 0.3. So now you know how to proceed. We have theta d, we have zeta. We can now use that from our table. That was in our performance specification table. We now have this case again. We can now solve for r. That's equal to this e to the minus zeta theta sub d, which is pi over 3 over square root of 1 minus zeta squared, with zeta equal to 0.3, and this ends up being 0.7194. So that now we have z squared minus 2r cosine theta sub dz plus r squared. R squared for this value of 0.7 ends up being 0.52. This value, now we might be a little bit off, as I said before, ended up being 0.7294 or 0.73. And maybe you didn't find that, but you can now look at what you have available to you, and one of those at least matches one of the coefficients. There's our 0.52, and 0.8 isn't too far from 0.73. Again, this is all sort of approximate. Now we have, if we complete the square, our pole location is 0.4 plus j 0.6. Did I give myself a chart? Maybe I didn't, but now we could go back to this chart and look at where we end up with respect to 0.4 and 0.6, and that gives us a zeta of 0.6, I'm sorry, of zeta of 0.3, which is what we knew to calculate from that. So that's now our answer that we would be selecting. I think it asks for a denominator polynomial. This looks like the same step response. So for the following step response, we've already found everything that we needed. Now we're asked to find z, the magnitude of z of our closed loop pole. Well, that we just found. Here is 0.52, that's r squared. So from previous, we now know that r squared is 0.52. R is now 0.72, and hopefully that was one of your answers to find the magnitude. How far are we away? And if we went back to this particular plot, and I've already erased what I had, but here we had a 0.4 and a 0.6, if I'm remembering my problem properly. You could now calculate using the Pythagorean theorem to find what that hypotenuse is. That's now 0.4 squared, or r squared is now 0.4 squared plus 0.6 squared. And that then would give you the correct r value when you take the square root. Oh, thought I was out of questions. I was hoping, but we have one more. Don't forget your questions. So now we have our last question, I think. Everybody did quite well on this one. This is basically just do some algebra with transfer functions. If g of z is specified and t sub c is given, what is the controller transfer function? Now we're simply finding or calculating c of z based on the formula that we know is true to create this transfer function c of z. And here we could have unstable pole zero cancellations in this process. That's where we want them to occur. We just don't want pole zero cancellations unstable between c of z and g of z. In this case, you might want to find t sub c over 1 minus t sub c first. And if you put that over a common denominator, you end up with z squared minus z minus 1 and z plus 1 upstairs. We now have what we need. Now we plug in g of z. And multiply that with what we just found. That factor, and that was now a cancellation on the unit circle. This is where we want those cancellations to occur during the design of our controller c of z, so that c of z is not going to possess this unstable factor that would try to cancel that in the plant g of z. And if you run through the algebra, you see you have 1 over 2, or 0.5. This pops upstairs because it's in the denominator of the denominator, and the denominator was z squared minus z minus 1. That's now how you can determine your controller transfer function given a g of z and a t sub c of z. What you want to check after in your real process, here you're done, that's you can find, but now you want to make sure that in c of z's expression, when you look at that compared to g of z, you do not want c of z and g of z's product to have any pole zero, unstable pole zero cancellations. That's the no-no. Hopefully that now gets you ready for your second attempt on quiz number 5.